Alexia. Now we are looking at example 8 on the design of shafts. So here the questions: a solid circular shaft is subjected to a bending moment of 3000 Newton meter and a torque of 10,000 Newton meter. So in these questions they have given us the bending moment and the torque. So the shaft is made of 45C8 steel, that is the type of steel, having ultimate tensile stress of 700 megapascal. So here they have given us ultimate, so remember never to use ultimate tensile stress straight away into our design calculations. And an ultimate shear stress of 500 megapascal. Now assuming a factor of safety as 6, find the diameter of the shaft. So here you have the diagram that I've shown. So you have the bending that occurs on about the x-axis and the turning moment which is about the z-axis. So we can work out the allowable tensile stress based on the ultimate by taking the ultimate tensile stress divided by the factor of safety. So 700 megapascal divided by 6, that is the factor of safety. So you have 116.7 megapascal. So then we continue with the allowable shear stress. So the allowable shear stress, you take the allowable ultimate shear stress here, 500 megapascal, divided by the factor of safety of 6. So you have 83.3 megapascal. So TE is the equivalent twisting moment. So in this case, we will be considering both the TE, that is based on the shear stress, and the ME, that is based on the tensile stress. So as I have mentioned earlier, if the question has given us shear stress, then we will have to consider TE only. If the questions have given us only the tensile stress, then we only consider ME. If, let's say, questions has given us both the shear stress and the tensile stress, or the normal stress, then we have to consider both the TE and the ME. So first, we calculate the equivalent twisting moment by taking in the torque and the bending moment. So you have to use the square root of m squared plus t squared here. So the bending moment is 3000 and the turning moment is 10,000. So from there, you got your TE as 10.44 kilonewton meter. Then based on TE, you can find out the diameter of the shaft by putting in the allowable shear stress, which is 83.3 megapascal. So from this, you will be able to find out the diameter of shaft that is based on the equivalent twisting moment. Then we goes on with the ME, that is the equivalent bending moment. So, and then this is the formula. So remember, the M represents the moment and the T refers to the torque. So putting in the value, substituting the value 3000 and 10,000, you will be able to calculate the equivalent bending moment, which is 6.72 kilonewton meter. And also from this, pi over 32 times d cubed, that is the diameter, multiplied by the allowable tensile stress or normal stress, which we have found that is 116.7 after dividing it with the factor of safety of 6. So from this, we will be able to find out the diameter of shaft under the condition of equivalent bending moment. So based on these two answers here, so as from the beginning of this chapter, we have certain examples that has proven that, okay, the greater the size, then the safer the design of the shaft is. So therefore, we have chosen the diameter of the shaft that is required for this design as 86.1. So taking the larger of the two values, so the diameter should be 86.1 millimeter, and this should be adopted as the diameter of the shaft that is required for the restriction or the limits of ME and TE. So this will be the safe design. So you can just round this up to maybe 90 mm and so. Thank you very much. That is the all for example 8. If you have any comments or any questions, please put on the comment section of my YouTube under the section of shaft design. Thank you very much and see you soon. Thank you. Bye.